recorded now? Good. Okay, I'm going to talk about the categorical case of the Hopf map, and this is part of my PhD project. But before doing, let me just do a quick review of principal bundles. So in the case of principal bundles, when we have a Lie group G and a topological space X, what we want to do is just to construct a topological space over X, such that it's locally a product space of G. And two easy examples are just a torus and the boundary of the Mobius strip over S1. So in the case of torus, two-dimensional torus T2, the basis space, we have a circle, and we can cover our circle with two opens U and V, and then we construct our two locally trivial data, which is U cross S1 and V cross S1, and we want to glue this data together along their boundaries. So if you want to do this trivially, for example, in this case, we get a torus. We just glue these two local data trivially. So we get a torus T2. And one non-trivial example would be when we have two copies of a circle, S1. So it's this one, for example, is S1 bundle or U1 bundle. The torus is a U1 bundle or S1 bundle over S1. And this here, we have a Z2 bundle over S1. So we have two copies of S1, and we glue these two circles. First of all, we cut these two circles and we glue them along their start and end points. So we get the boundary of the Mobius strip. So this one would be a trivial example, a trivial S1 bundle over circle. And this one is a non-trivial Z2 bundle. So it's a non-trivial Z2 bundle over S1. And formalism for doing this is just constructing some gluing data, which contributes to a check co-cycle. So a check co-cycle, when we want to construct this check co-cycles, we take a cover of our basis space, the cover of X, and then we try to define some smooth maps from double intersection to our fiber or structure group, which is in this case is G. And this here should be an element in UI in the first check cohomology group. And once we have this gluing data, we can construct our total space of our G bundle. We just take P as disjoint union of our locally trivial data, which is UY cross G. And then we try to glue this together. So say we have an element U and G should be equivalent to U and Gij of U multiplied by G, the action of our group G. And this one is an element in UI cross G, and this one is an element in U, J cross G. So we glue this data together like this. So we have these two examples, and then I'm going to discuss a non-trivial, a review of the half map, which is a non-trivial U1 bundle over S2. So in real coordinates, we know that we can write the half map as this. It sends a point X, Y, Z, W in S3 to a triple like this. And in the framework of our construction, it's more appropriate to consider the half map in complex coordinates. So in complex coordinates, if we consider S3 as sitting inside C2, we know that S2 is homotopy equivalent to CP1, the complex projective space, and the formula for the half having complex coordinates would be sending a point Z1 and Z2 to its class in CP1, which is Z1, Z2. And our goal here is to categorify all of this construction. And by categorification here, I mean, we want to construct. So in the ordinary case, we have a G bundle over a topological space X. And when we want to categorify this, we want to get a map. Instead of a topological space, we want to get, sorry. In order to we want to get a categorical space here instead of a topological space, and I will tell you about the definition of a categorical space. And we don't want to change our basis space because we are interested in the action of some Lie groups on our basis space. And we want to, instead of having an ordinary group, we want to get categorical or strict categorical group Khalili. So our fiber would be a two group or categorical group if you want. So before going to detailed construction of this, let me provide some motivations for this. First of all, if you pay attention to the construction of the half map, according to the half map, if we quotient or mod out S1, the action of S1 on S3, we get CP1. And from here, we know that we can interpret representation of SU2, the two group SU2, as space of global sections, of line bundles or line bundles over CP1. And if you want to do the same for the string group, and why we are interested in string group, we know that SU2 is a fundamental in representation theory of Lie groups, and the hope here is, the guess here is that string 3 plays the same role in representation theory of categorical groups in the two groups case. So once we construct our categorical Hopf map, we'll see that this two group or this categorical group string 3 would be the symmetries of the categorical Hopf map, and we can interpret the representation of this string 3 as a space of global sections of categorical line bundles over CP1. Because after constructing our, say, our categorical Hopf map, string 3 would be the quotient of string 3 by here our structure group, not the circle itself, it's a categorification of circle, which is curly U1. And I will talk about this curly U1, the structure of curly U1. It should be CP1, the quotient, because of this, or this 2. So we can interpret the representation of a string 3 as a space of global sections of categorical line bundles over CP1. And the other motivation for going for the categorical Hopf map is just categorical analog of Mackay correspondence. And what is that? We know that finite subgroup of SO3, the rotations in R3. We have five finite subgroups, which are cyclic groups, dihedral groups, tetrahedral group, octahedral group, and icosahedral group. And we know that spin 3 is a double cover of SO3. So if we extend our SO3 by ±1 or by Z2, we get finite subgroups of spin 3. So here we get, for example, C2N. Here it's again cyclic group. Here we get binary dihedral group. Here we get binary tetrahedral group. So here we have 12. Tetrahedral group is rotations of tetrahedron. So it has 12 elements. Octahedral group has 24, and icosahedral group, rotations of an icosahedron, has 16 elements. So here we get 24 elements. For this we have 48 elements, and for double cover of icosahedral group we get 120 elements. And now if you want to after constructing a categorical Hopf map, from curly P to S2, we know that we have an action of SO3 on S2. So we have finite subgroups of SO3. We have finite subgroups of spin 3. And now we want to get the categorical analog of this, which is finite subgroup of this categorical space. And by categorical space, I mean just a category in which the objects and morphisms are both topological spaces. That's the definition of a categorical space. So how we can get a finite subgroup of curly P over string 3? We just need to extend. So here goal would be getting finite subgroups or finite categorical subgroups of curly P over string 3. So for doing this, we just need to extend these finite subgroups, for example, say binary tetrahedral group by some categorical or some finite categorical subgroups. Says, and what do I mean by this notation? It's a two group or a categorical group with its objects. It's just a trivial group, and its morphisms are just CN. I mean, from 1 to 1, we have elements of our cyclic group. So in this case, we can construct finite subgroups of a string 3. Of course, this n depends on the order of our group here. And the other thing for motivation of the categorical Hopf map would be, yeah, after we construct this finite subgroups of a string 3 or curly P, we guess that these finite categorical subgroups would be just categorical analogs of Platonic solids. We know that we have 5 Platonic solids: tetrahedron, cube, octahedron, dodecahedron, and icosahedron. And so if we say we have constructed our categorical Hopf map over S2, so if we take tetrahedron described inside S2, if we consider our map after extending this tetrahedron, we get some kind of categorical object inside curly P, which the rotations of that categorical tetrahedron would be just this element here, this categorical group here. This is just the symmetries of categorical tetrahedral group or tetrahedron. And the final motivation here, for example, is the string 3. If you're familiar with the construction of a string 3, the usual construction that people usually use for string 3 is just we have the Lie group spin 3, and we extend that by CP infinity to get string 3. But the thing here is that if you do this, as you know, we get infinite dimensional group here. But if we want to get a finite dimensional model for string 3, instead of it's by Schumer-Priest. So you can extend spin 3 by the categorical group BU1, and by categorical BU1 or this notation, which is more usual in literature, U1. So it's again a 2 group with objects, the trivial group, and its morphisms are just elements of the circle. So for each arrow from the trivial group to trivial group, we have an element corresponding to an element in U1. So it's again with this string 3. And do you have any questions so far? Okay. Good. And yeah. So as I was talking, we want to categorify all of these constructions. So we need to construct our curly G corresponding to the circle group. We need to construct our total space or categorical space. And as I said, we don't want to change the base space. It's still a topological space because we are interested in the actions of, for example, SO3 on the base on the S2. So we don't want to change the base space of Hopf map. So but before going to the categorical case, let's remind you of the definition of cross module associated with Khalili G. So it should be, it's a 4 tuple. We have 2 groups, and alpha would be the action of an action of G on H, and beta is just a group homomorphism from H to G, satisfying some conditions. But if we have a topological, if we have a so given a categorical group curly G, we can construct a cross module associated to this categorical group. How can we do this? We can put G as objects of curly G. We can define H as the kernel of the source map. And what is the source map? It's map from morphisms of curly G to objects of curly G. And alpha here in this case, let's me to another page. Yeah, alpha beta in this case would be just the restriction of the targets, restriction of the targets map from morphisms of curly G to objects of curly G, because we know that once we have a morphism in curly G, it has a source and it has targets. And to H, and the last thing would be alpha, which can be defined as trivially from G multiplied by H to H. And this alpha is just yeah, this alpha is just this one. So we know that the categorical group is just a monoidal groupoid. So we need to define our tensor product or monoidal structure. So alpha, if G wants to act on H, it's under using this action. We have identity of G. This is the tensor product or monoidal product in our monoidal groupoid, and this is our H. And this is identity of G inverse. And so in this case, we get a cross module associated to our categorical group. Now, as I said, we want to get something in H1 of X with coefficient in Khalili G. Why? Because just as in the ordinary case, when we have a principal G bundle, where G is a Lie group, we want to define a co-cycles, satisfying some conditions because they want to be in this group, the first check homology group. And here, elements of this group, this check homology group, would be a triple, say WI. This WI is again a cover of our basis space X. We have some maps from Gij, some maps on double intersections, and some maps on triple intersections. And what are properties for elements here in H1 of X with coefficients in Khalili G? So first of all, the codomain of our Gij should be this G in the associated cross module to our Khalili G, categorical group Khalili G. And the codomain for smooth maps Hij,K should be the morphisms of our cross module. And the properties these maps needs to satisfy is very similar to the ordinary case. It needs to satisfy some co-cycle conditions to contribute to a class in H1 of X with coefficient in Khalili G. So after defining these smooth maps on double intersections and triple intersections, we are ready to construct our total space. It's again very similar to the ordinary case. As we've seen, we have some local data and we want to glue these local data together. So we construct some disjoint unions and we glue these disjoint unions. Now we have a categorical space. So we have objects and we have morphisms. So we need to produce a local data at two levels. So at the level of objects, we take our disjoint union as disjoint union of our cover across the group, the objects in our cross module. And at the level of morphisms, we get the disjoint union of double intersections cross H cross G. And this H again is our objects, our morphisms in our cross module. So if we have and the gluing data here, it just if we have a map from, say we have a map WHG in here, so its source is WG, it's an element here, and its target again needs to be in objects. So we define that as W, then Gij W inverse, the inverse of Gij W, and then multiplied by beta of H, and beta of H is just, as you know, as we remember, this beta is a group homomorphism from H to G. So beta of H is an element in G. So we have this element. So it's the thing that's glue. Of course, we don't need any gluing data at this categorical construction because we just, in the case of categorical constructions, we just need equivalences of categories, so we don't need any gluing data, but this construction, this map from an element in objects to an element in objects, which is a morphism in this, gives us a kind of gluing gluing data for gluing this data together. So similar to principal G bundles, when we have an action, we have a principal G bundle, we can take the quotient of our total space by action of our group, our structure group. Here again, we can define an action of our structure categorical group on curly P, and then we can mode out just we can take the quotient of curly P by curly G to get our base space. So now we want to construct the corresponding corresponding categorical group to circle group. So how can we do this? We have the circle group here, and we extend this circle group by the categorical group BU1, and then we get the categorical circle. And what are the elements of what are the structure of this categorical circle? First of all, it's a monoidal groupoid. So we have objects as R, real numbers. Morphisms are just a semi-direct product of Z cross R over Z with R. Why is this case? Because associated cross module to curly U1 is just R, Z cross R over Z, alpha beta. And here alpha is just the action of R on this. It sends an element here to M and A plus RM. And beta is just the group homomorphism from this, sending an element here to M. So the usual way that we get categorical group associated with cross module is defining objects as objects of our cross module, and then morphisms is just a semi-direct product of objects and morphisms. So here a morphism from so a morphism here in Z cross R over Z semi-direct product with R would be from R to R plus N, because it's R plus beta of MA. And the other thing that we want is, now we want to cover of our base space. We need to cover our base space to construct our total space. So we can take this cover of S2 with 6 patches. So we have V1 as points in S2 with X positive and V2 with X negative and vice versa. So after taking this cover, we can construct our categorical space, our total categorical space of the Hopf map using this formalism. So we have our cover of S2. We have our group G associated to curly U1. Here we have double intersections. Here we have our group H, and here again we have our group G. So this would be a disjoint union of 6 tori. So that's the total space or total categorical space of our categorical Hopf map. And the other thing that we can discuss is just, as I said, for completing a construction, we need to define some smooth maps which contribute to the co-cycle in H1 of S2 with coefficients in KLU1. So for the definition of this GIJ and HIJKs, the usual cover of when we want to construct Hopf map, the usual cover that we take is we have this S2 here. So we take the upper hemisphere and lower hemisphere. So the intersection of these two would be homotopy equivalent to the equator, which is a circle. So for constructing these smooth maps, we just take a cover of S1. Why? Because as I said right now, it's just the intersection of upper hemisphere and lower hemisphere would be equivalent to homotopy equivalent to the equator, which is a circle. So if you want to define a map from double intersections, say, from double intersections to R, what can we do in this case? We define maps from double intersections to the cover of circle, and after doing this, from the circle to R, we can define our maps using this map kappa here, which is using just because the cover of circle is just consists of some kind of arc. So for going from here to R, we just need to doing some arc sine and arc cosine to get rid of this sine and cosine on our circle. So that's the usual definition. That's how we can define our GIJs. And as I said, because we are interested in the cover of our circle, here, after defining this 1, 2, 3, 4, 5, 6, 7, 8 maps, we can define all other maps to be 0. I mean, at the level of double intersections, because after that we can check that these smooth maps satisfy co-cycle conditions in the H1 of S2 with coefficients in KLU1. And for triple intersections, we can again use this cover of S1 and cover of S2. And this is the cover of S2 here. And the cover of S1, as I said, we use this cover, this 4 cover of S1. And now that we have constructed our smooth maps, which is an element in H1 of S2 and KLU1, we want to prove that our categorical Hopf map is not a trivial KLU1 bundle. So we do this after Yeah. First of all, let me explain factorization of our categorical Hopf map. By the Hopf map and a bundle gerbe over S3. And what is this map? We have a bundle gerbe over S3. We have S2, and it's our categorical Hopf map, and it's eta. So what is a bundle gerbe? Let's quickly review the definition of a bundle gerbe. So if we want to construct a bundle gerbe over S3, we need a surjective submersion over S3, which people usually take this Y as disjoint union of elements in cover of S3. And we also need a line bundle over the fiber product of Y with itself. So it's Y cross Y over S3. And we also need a multiplication for our bundle gerbe, which is something like this. And by pi ij here, I mean map from Y3, the fiber product of Y with itself, but we need to do it, it's Y cross Y cross Y to Y2. So here we get a line, L is a line bundle over Y2. So here we get a line bundle over Y3, a line bundle over Y3, and a line bundle over Y2. And in this, for the sake of the time restrictions, I don't want to talk about this multiplication, but the usual way of getting this bundle gerbe. So we want to construct a bundle gerbe over S3. So we define Y as objects of curly P and L as morphisms of curly P. And we can check that L would be a line bundle or a U1 bundle over this fiber product. So this map H is what I was talking about, the bundle gerbe over S3, and this is the usual Hopf, the classical Hopf map, and this is our categorical Hopf map. So now how can we prove that our construction is not a trivial curl U1 bundle? Why this map is not a trivial curly U1 bundle? The reason is that if we take our smooth maps Gij and Hijks and compose them with a map from here, this map is just the universal cover of S1, and this map is just the say the trivial map, sending every element in Z cross R over Z to 1. If we take these smooth maps and we construct a bundle associated to this data, we get a U1 bundle. Why a U1 bundle? As you can see, we have S1 here, and we have the trivial group here, and this is the cross module associated to cross module associated to U1. So we get a U1 bundle, which is equivalent to the Hopf map. And that's one easy way to see that our construction is not trivial. Another way is just using the associated class to our construction in this group. So if we take our construction, our class of our co-cycle here, it's it can be seen that it's not trivial co-cycle here, but for the sake of time restriction, I don't want to talk about this, but as I said, this is an easy way to see that our construction is not trivial. So the whole thing that I talked about during this talk was construction of the Hopf map and some motivations for that, and seeing that it's not trivial. It's not a trivial Khalili U1 bundle. The other thing is that it's also it has a beautiful factorization using the classical Hopf map. So I think that's it was all of that I wanted to talk about. And if you have any questions, I would be happy to answer.